Hello, everyone. Hello, everyone. My name is Oleg Selajev, and I'm very, very happy to be here at the J4K conference. Today's session topic is testing and monitoring GraalVM native images. And I'm currently not affiliated with Oracle or the GraalVM team. I was on the team for quite a while, so I think I have a good understanding of what I'm trying to talk to you about here. And if you have any questions or any follow-ups, or you want to argue with me about certain things, then please find me online. I go by @Selajev almost universally, GitHub, Twitter, all that. So without further ado, let's start. Just recently, a few days ago, this is actually my 4th day at the new job, I joined the Atomic Jar startup as a developer advocate. You can find them online. It's a very exciting, interesting community. We're trying to make integration tests better, which also kind of works with the topic of the session a little bit, but I promise you this is not intentional. It's slightly intentional, but this is this is not the main point of the topic here, right? Let's go. GraalVM. GraalVM is a high-performance runtime that revitalized Java ecosystem a few years ago. It comes with the state-of-the-art just-in-time compiler that can speed up your Java applications. The same compiler can be used ahead of time in a setting where you can generate the binary out of your application, and that binary will exhibit a different performance profile, which is really, really good for typical cloud deployments. That's why people in the Java ecosystem very much embraced GraalVM, and we're very excited. Many projects got support for that. And this is what we're going to talk about now, right? So the technology behind that is called GraalVM native image, and it can take your Java application, and then it can process it, and it can output a binary file that will be standalone, that will start really fast, and that will work with much tighter memory constraints than you would expect normally from a Java application. So now this is a little bit different mode of operation, how you deploy your applications compared to how you normally operate Java applications. There are some constraints. There are some interesting things that you need to know about the build process. And today I want to talk to you. For many times, we had sessions about GraalVM, how to build native images, how they speed up your deployments, how they work very well in the cloud. And this all very nicely can be summarized in actually one picture. Ahead of time compiled binary have great speed, startup speed, have much better memory footprint than your typical Java applications, and come in small packages. This is very nice, and this is how it works. Currently, I think we reached the stage where you can just say that native image is mostly just works for your applications. There is support for native image compilation in most popular and common Java frameworks. Probably the most important one is Spring, and there is a Spring native effort which gets better and better every month. Just a few days ago, Sebastian Deluze, the lead for that Spring native project, announced that they have a milestone for the next release and asked people to test and showed the good optimizations with the even smaller memory consumption, better startup, something like this. So I think we're past the point where we try to make native image work for your code, and we are trying to figure out how you can enable native image as a part of your workflow, and how you can deploy and monitor and work with those binary files further, besides just building them and like looking in how quickly it starts up in like 20 milliseconds. Like, oh yeah, perfect. Yeah, it starts up quick. What do you do next with it? So let's assume that it just works. Now we have 3 parts of what we want to take care while we talk about the native image, sort of the operational principles. So first, we need to build the native image. This is interesting. And this is interesting because when we talk about the normal Java runtime with a space, when we start our Java application, it starts and then it runs, and it's one single process. And that one single process does everything there is to do with this running this Java application. So when we test our Java application, for example, we test this running process. When we want to monitor Java application, we talk about monitoring this particular running process, what it does, how much resources it consumes. We are doing things in process. This is also mirrors how we actually scale our Java applications. We scale them by thread within a single process. So normally we scale Java applications by giving them bigger hardware, stronger, more powerful machines, and just saying like, oh, you run more threads, or here you have more memory. Just figure out how to use this the most appropriately. Your GC is amazing, go with it. So now when we talk about the native image, there are two distinct phases. One is the building time, the build time, when we actually take our application bytecode and feed it to the native image utility for the analysis, for crunching, for compilation, from pre-initializing the classes of our application to create this binary file that will be our deployment unit. And then we actually run that application. And those two processes, they can be separated both by geography, right? We can run them in different machines on different networks. We can build one in a Docker container on your local machine and then throw it into the AWS Lambda on the other end of the world, and it will be there. And they also can be separated by time, right? We can build it once and then actually we start it later many times. It could be several times as well. It doesn't have to be like a single runtime corresponding to a single invocation of the build. So there are two separate processes, and the top one, the build time, is technically a normal Java application. This is the normal run of a Java invocation. There is a Java application that loads your application, looks at the classes, does everything. The GraalVM project in general operates very much, it's written in Java, and it operates like all the components operate like normal Java applications. So that is normal Java. That gives us quite a bit of ground there because we know how to handle that. We know how to instrument that. We know how to debug that. We know how to give more or less resources for that. And then there is the second part, which is the application, right? And that is the binary file, which we would like to figure out how to test, how to monitor, and how to be sure that that application actually does exactly what we want to have. So this is the important part. When we build, yes, there are all kinds of configuration issues that you need to take care of. So for example, some dynamic parts of the Java language need to be explicitly pre-configured by the developer or by the application framework. So if you're using something like Micrometer or Quarkus or Spring Native, they will provide configuration for some of those features. And these are the dynamic features that the static analysis of the native image cannot see through by itself. So this is reflection and accessing classes through the reflection without, well, like you can do that dynamically at runtime. And if the static analysis cannot see which classes you want to access, it just cannot process them properly. It is creation of JDK proxies. It is accessing the resources. That configuration needs to be there. And this is very important. Because you can provide that manually. Your frameworks and your application libraries can provide that for you for their parts, of course. And there is also a tracing agent that can record the usages of those functionalities and output the configuration for you. So there is an automated way to provide this configuration to ensure that native image build will include the relevant parts and will be sure that what code path will be taken at runtime so the build succeeds. However, at the end of that build, of course, there will be a binary file. And then we can run that binary file and hopefully it does what we want. And in most cases, it does what we want. But what we need to do, we need to make sure that it does what we want, right? We never, like as developers, we never trust the code, and especially if it works. Like if something works on the first try, that's suspicious, right? Like you have to see things fail before you can fix them and then be sure that they're fixed. So we go through this process, we get the binary file. What can we do with it? We want to test it. We want to verify that it actually corresponds to the functionality that we wrote, and that is actually corresponds to the functionality that we wanted to create. Those are very different things, two very different things normally. So how do we do that? How do we test GraalVM native image applications? Well, fairly simply, right? How do we test Java applications? We have one process and we run tests against that. Usually tests are represented either, and the different kinds of tests that we run are represented either by a pyramid or by a honeycomb like this. And I think the honeycomb abstraction here is much more interesting. So there are some tests that test the implementation details. It doesn't make sense to create very many of those, but they are very useful for the components where there is an internal inherited complexity, and those components are largely isolated from the other components of your system. This is what we call usually the unit tests. They test the implementation detail. Do I multiply the matrices correctly? If I reverse the string, do I forget the null termination character or not? And so on. There are integration tests, which according to the honeycomb and according to the Spotify engineering block, should be the bulk of your tests. They verify the behavior of your system or a component in integration with other components and other systems, but they do not depend on the internal state of those systems. So they verify that your application, your microservice works with the database, but it doesn't test the or verify that the database is implemented correctly. Or for those things, you have the integrated tests, which also kind of sort of end-to-end tests, and which generally are considered not the best idea, at least to have a lot of them. So in the Java ecosystem, we have the JUnit tests and other unit test frameworks for the implementation details tests, and then something like test containers or any other means that you want to write for the integration tests. So test containers is generally a very popular Docker-based approach to create integration tests, where you can manage the lifecycle of your dependencies and third-party systems programmatically through an API. And then we're not going to talk about integrated tests because they sort of, not everyone likes them. And I think since they test your system with other systems in isolation, and not in isolation, sorry, in like together, you can do that with any other means. So it doesn't depend whether you run Java or you run your native image. You just throw it in production and sort of hope that it works, and then somebody will tell you if not, or staging, anything like that. So how can we test native image apps? We already have two parts. We have the Java source for the application, and we have to test Java source, right? We have to test our Java application as a Java application. We have to run our unit tests. We have to run our integration tests. Those things will verify that our application does what we intended it to do, right? So it doesn't, like, it multiplies the matrices correctly and accesses the correct columns in the database and sends messages to Kafka when we actually wanted to send messages to Kafka, and so forth. And then we also want to verify that that functionality is preserved and is not broken, and the configuration that we provided to the build is sufficient and comprehensive to ensure that all the code paths that we want to execute at runtime will still be executed without any errors. That this transformation, this build time to runtime transformation, didn't break anything in the functionality that we wanted. So how do we do that? For the unit tests, for the implementation detail tests, there is a project called Native Build Tools by GraalVM. This project consists of mostly Maven and the Gradle plugins that simplify your application lifecycle when you want to make it work with your native image. So what they provide is they provide you with functionality to compile your application as a native image, provide the configuration, provide the class path, correct class paths, and so on. And they also provide you with the ability to run tests in the native image mode. So you can take your unit tests, you run them once on the JVM using normal Surefire plugins or normal means to run tests. And then the native build tool plugin will record the necessary configuration, will figure out which tests you run, will, if necessary, will provide you with the configuration generated during the test run on the JVM. So if you use some reflection or anything, it will simplify your build process. And then it will build the native image with your test code. And then it will execute the same code path in the native image mode. So you can run with just adding the build plugin to your Maven or Gradle project. You can run your unit tests in the native image mode. This is a fairly new development. I think the native build tools were announced back in summer, which is not a lot of time back. And this is an excellent opportunity, especially so currently I'm mostly focusing on application development, where you have your application, something that you actually run further. But if you're writing a library, if you maintain a Java library, then using native build tools plugins is an excellent idea for running your unit tests in the native image mode. And then you can safely say, yeah, I know I've seen the code paths that are executed from my normal Java unit tests pass also in the native image mode. Right, so they will hopefully pass in the, barring any modular any actual bugs, they will pass in the user applications and user applications. So you run the tests, you record which tests you run, you record the configuration, you compile the native image with the entry points from test methods, and you run them. And they run the same way. You can run them in CI. Probably you want to not, it could be a little bit time-consuming process, especially on the very limited hardware, if you are using like the open source available for free runners. But you can maybe run those jobs once in a while, like a nightly job, maybe, or something like this. You don't have to run them on every PR. So all in all, you can run unit tests just the same, and they provide you with quite a big of a margin of confidence that your application is doing what it's supposed to be doing well in native image mode. And then for the integration test, you still probably want to use something like test containers. And if in the Java world, you have your Java code that you're running, which is the test and application code together, and you run your code, and the test containers manages the third-party dependencies, which are typically our databases or your Kafka instance or your Elasticsearch or any third-party API that you're relying on. And the lifecycle of those is managed using the Docker containers. And you run the test in Java mode. And you should run them anyway before you start running them in the native image mode. But for the native image mode, you probably want to enhance this picture a little bit. So this is my current understanding how to do this. And probably what you want to do, you still want to use the test containers, but you transform your integration tests into something a little bit more complex. You still want to have them for individual tests. You have to have this ephemeral, lightweight, reusable or like throwaway containers for all the dependencies and your application as well. For all the dependencies, but also for your application as well. Since native image of your application is a binary file, literally, it's a standalone binary file. You can put it in a very simple Docker image. You can put it into the Docker image that starts in milliseconds because your application is pre-compiled, so it starts really, really fast. And then you drive the other tests, which probably you need to use through some sort of an API, which is okay for the applications. It's a little bit harder for libraries. I'm sure you can expose some things there, but you drive your API and UI tests, and you use your application within another Docker container. You're going to deploy it to the cloud anyhow. It will run within some sort of a container, most probably, either that is a serverless solution, or this is just your own Kubernetes cluster, or you're running them on just in the containers, or even if you run them on VMs, you can mimic that with Docker container. And because the structure of that Docker container is so simple, it's literally just the operating system and your application, you can create it programmatically with the application that you pre-built, and you can set up a new instance of a test and a new instance of the application literally for every test, because it just takes milliseconds to spin up a new instance of a Docker container for your app. So this is how I think you should do the integration tests. And then, yeah, it's a little bit similar to the end-to-end tests that we are probably not want to encourage. But since you can use the throwaway setups, so you don't depend actually on the implementation details, whether databases or Kafka correctly processes your things. You just verify that you work with them and you can correctly send data to there or read data back. Right. And then the third part there, what we want to talk about is monitoring your GraalVM native image application when you deploy that. So here is this a caveat, a problem, an obstacle of sorts. Very many tools in the Java ecosystem, when we talk about monitoring tools, they depend on the JVM tooling interface and the Java agent approaches for monitoring your application. What literally happens is you provide an instrumentation agent to your application, and then it does its things, interfering with the work of your application. It instruments your classes, it can add some timestamps, or it can add some filters to your application, and then the logic of those will be implemented to gather the data and sometimes send it back somewhere to the backend for monitoring purposes. This is how you normally do this. Even if you don't do this, probably your framework of choice provides integration with certain monitoring solutions, and they can enable that, and you can just enable configuration, but the outcome will be very similar. This approach doesn't work very well with the GraalVM native image, because when you have the application pre-built, it's sort of immutable. It's a native binary, and you cannot instrument the bytecode there to when the classes are loaded, because first, there is nothing that loads classes. Second, part of the classes are initialized already, and nobody knows in which state they are, because that is an implementation detail, right? So there is no hooks to add the Java agent to instrument and add the monitoring to your application, which means that you have to add the monitoring things at the stage where you can do that. So one library for monitoring that works very, very well for native images, Micrometer. I know, of course, all the frameworks, most frameworks of interest support Micrometer and have starters and instructions how to enable Micrometer. The thing is, you enable your own monitoring and metrics in your application, and you do that ahead of time as well. So when you build your native image, you already know that you're going to need the metrics, and you can say, please enable the Micrometer support. So the code that Micrometer or that another monitoring agent would be inserting in your application, it will be there available during the build time, and it can be correctly processed and compiled with your application. So then of course, yeah, you just deploy your application, the library is there, the application is using that library, and it works. This is a little bit inconvenient, or rather, it's not inconvenient. This is a little bit maybe unorthodox for when we think about how we deploy and manage Java applications, but it's definitely not something that we do at all. For example, if you think about how we monitor and run Go applications, Golang applications, or any other precompiled applications, we do embed the code that we want to send the monitoring messages away. We do that at the build time, and we do that manually or with the support of a framework, of course. Right. So you use libraries for monitoring. What you can also use the J4 recording things for monitoring the vital properties of your deployments. What you can do is, and this is the recent addition to the GraalVM native images, you can build your native image with the J4 recording functionality integrated into that. And then you can, when you run it, you can say, I would like to output, I would like my J4 recording file in a certain place. and then it would enable that, and it can generate that GFR files snapshots for you, and then you can analyze that. So this is how it works. Currently, I think they mostly supports custom events, which is a little bit similar to gathering the metrics from using other libraries. So you can instrument your code and say like, oh, emit this event, measure the timings. You also have some event types that are normally supported about the Java virtual machine and the versions and the memory management, but not all of them. But custom events definitely work. So if you really want some information about what happened in your application run as a native image, you can definitely enable that and experiment with that. It's fairly simple to do. Right. And then, of course, so currently, I don't think it provides very much the garbage collector, memory, and CPU monitoring values. They're just not implemented. Maybe they will be implemented fairly soon. And then since you deploy your applications using containers, anyhow, you can manage normal Java configuration options for memory should work, right? So you can configure the maximum heap and minimal heap and the sizes. I think I'm back. There was a glitch in the internet, right? So one thing that you want to configure is memory, and yeah, you have the options to do that. You have the options to configure the memory usage to a certain extent during the build time. And this is something that you definitely want to do, especially if you want to run it on powerful machines and not limit memory not artificially on the higher level. Like if you don't limit the memory of a Docker container, then just do the memory configuration for your application level. So that's it. I think this was a very quick rundown of how I think testing and memory and configuration could be done with GraalVM native images. I think it should cover the most typical use cases and provide you with some confidence that when you deploy your GraalVM native image, that it works the way you expect it to work. Right, we have a question from the QA. What's the performance difference between Spring Reactive and Quarkus Reactive with GraalVM? Right, I'm still here. I'm still on the Zoom. Very good. Right. If I understand correctly, I don't think there is quite a bit of difference between the performance of Spring Reactive, Quarkus Reactive as the libraries. So I think Spring Reactive depends on Reactor project, and Quarkus has their own implementation of the reactive extensions called Mutiny. And they're like different implementations with probably different trade-offs and how easy it is to start it. I don't think there should be a major performance difference. If you talk about your applications in general, right? So if you write a microservice using Spring Reactive approach Webflux, and if you write a reactive application with Quarkus, there might be differences, but I don't think they kind of the source of those is the implementation of the reactive libraries, right? It's the source of those is how well the certain application framework optimizes for this closed world assumption that GraalVM native image imposes. And think about this. This is so when we package our applications and throw them into Docker images and then run those containers, the applications become immutable. The class path is fixed. There could be certain classes that, well, the functionality is fixed and the class path is fixed. Everything is fixed, right? If you know that it's fixed and if you disregard that certain new things can come during the runtime, you can optimize your application. For example, you can limit which classes you use only once at the startup. If you don't have to use those classes, you maybe don't have to use the memory to hold those classes, and then you can get more memory for your business processes of application, right? If you optimize certain frameworks, then the impact is cumulative across the things. So I don't know what is the difference about performance between Spring Reactive, Quarkus Reactive per se, but if I would say, like on like a wild guess, if there is a difference, that probably comes from how the frameworks optimize for the closed world assumption, which I know Quarkus does very, very well, and Spring native team works very hard to do the optimizations for that. Right. If you have any more questions, I'd be happy to answer. If you don't catch me here, then I will see you online. It was a blast. I hope this session provided some insight and maybe gave you some philosophical thoughts about how to do testing. I strongly encourage, if you can take one thing out of this session, is that two things. First, use test containers for integration tests. It is a very good project. It's pretty amazing. And the second, if you are maintaining Java libraries, please consider running the native build tools plugins on them and trying to run good unit tests with in the native image mode, because that will be a big help from the community and for the community and for the ecosystem. Anyway, thank you very much. I don't think there are any more questions coming up. It was a pleasure, and thanks. Bye.